Okay, so let's restart and then we get more people in maybe 1 minute. So Axel, the floor is yours. Thank you very much.
So first I would like to thank the organizers for this fantastic workshop. And today I'm going to talk about graph neural networks and how to apply them to solve certain kinds of combinatorial optimization problem. So this week we have been talking a lot about graph neural network and typically message passing graph neural networks. And typically what you get inside is a graph with a vector of features for every vertex or every edge. So this is exactly as before. And at the end, you have a readout layer that gives you, let's say, one scalar for each vertex or for each node or for each edge and things like that. And that's the tasks we have seen up to now were mostly to predict something, well, just one single response for the whole graph or something for each node and things like that. In applications in operation research, typically what we are going to want to predict is a combinatorial object. So for instance, we may want to predict, let's say, a spanning tree on the graph. And the question is, how do we do that? And the way we have been doing that for a while now is that we have used a different kind of readout layers. If we want to predict, for instance, spanning tree with our graph neural network, what we are going to do is to introduce at the end a combinatorial optimization algorithm. For instance, here, a maximum weight forest or a minimum weight spanning tree algorithm. And typically, we are going to run cross-call algorithm on the output that we had of our graph neural network to predict this spanning tree. And so basically, this gives the ability to predict combinatorial objects on our graph using our graph neural networks. And so what I'm going to talk about today is that first, what can we do with this kind of architectures? Why would we want to predict combinatorial objects with graph neural networks? Then in terms of I talk a bit about the different architectures we used. And then how do we train them and which guarantees we can expect on this kind of applications. So basically, we will touch upon many things that have been discussed this week, but to make predictions with graph neural networks on combinatorial space. So let's start with some application. Why would we want to do that? So during the last 5 to 10 years, there have been many applications, and we can summarize them in 3 main kind of applications. The first kind at the bottom would be data-driven optimization. For instance, let's think you have an image of a map and you want to compute the shortest path from the upper left corner to the lower right corner. This is typically a graph problem, but you don't have a graph at the beginning. And so what you use a convolutional neural network, not a graph neural networks, to get the cost on the different edges, and then you use the extra algorithm to decode it and you train it. But I'm going to focus more on the 2 other kind of applications, which are contextual stochastic optimization and multi-stage stochastic optimization, which are important applications in operation research, and where this kind of graph neural networks have a bit changed the state of the art. So let's start with contextual stochastic optimization and with an application for an airline. So suppose you are an airline and you want to solve the aircraft routing problem. So each vertex of this graph is a flight. And what you want to build is the sequence of flights that are going to be operated by the different airplanes of your airline. So this is a very classic operation research problem. And if you take the deterministic version where you want to minimize the fuel cost, it's very efficiently solved with MILP, for instance. Now, as some of you know here, sometimes airplanes are late. And so what happens is that basically if your airplane is going to do V2 after V1, and V1 is, the delay of V1 is bigger than the slack between the 2 flights, basically the delay is going to propagate. So this makes your problem stochastic because this cost of delay are huge for airlines. And so you get an objective that is both stochastic, non-linear, in a very coupled way. And so basically there was no good algorithms to solve that, because you can formulate it as a stochastic optimization problem, but the algorithm don't scale. And basically the problem came from Air France, where they told us, well, we want to solve the stochastic problem to just manage the risk of delay, but you have the right to just one shot of a deterministic algorithm that takes all the time we need. And so what we did, so at the beginning we put a generalized linear model, but the thing is we wanted to keep the deterministic algorithm, which was a MILP at Air France. This is a slight simplification. And we used a neural network, then a GNN, to predict deterministic weights on every arc of the graph. And at the end, we just have to solve with the deterministic solver, and we get good prediction. And we were surprised by the fact that it gave excellent performance in practice, and the flexibility of graph neural networks enables to put some context there. Typically, we now use the weather forecast for the next day to be able to put as an input to our GNN to get routes that take that into account. And so basically, that's mainly the main setting we are going to look at today, which is the one of contextual stochastic optimization. So instances of your problem are denoted by X, and the instances may have some additional context information. Think about the weather forecast for the airline problem. You have, for each instance, you have a set of feasible decisions that depend on the input. Basically, the flight routes you can do depend on the flights you have to do. And the final cost depend on the noise, the random variable psi that you don't know at the moment where you take the decision. And what you want to do is a policy pi that is going to map a context to a decision. And typically, what you will want to do is to find the policy that minimizes the expected cost, the expectation being over both the instances and the noise that you may have in addition to the context. And one assumption that we often have in that case is that the difficulty, the combinatorial difficulty, comes from the fact that the problem is stochastic. If you know the scenario, then you have a reasonably good algorithm to solve it. So this gives the first kind of application, contextual stochastic optimization to manage uncertainty. Yeah.
So in the application with Air France for the flights, you're solving one single optimization problem at the very end, or you actually like iterate the thing? That's a decision that is taken for the next few days. So we solve it only once for the next few days, and we don't. It's not dynamic. It's a one-shot decision. The dynamic case comes right afterwards, where, for instance, for dynamic problems, think about fast delivery. So typically now, suppose that you have, when you book something, you have 2 hours to deliver a parcel. How do you organize yourself? This is going to be a vehicle routing problem where you have a depot, you have the different requests to serve, and you are going to build the roads that are going to be followed by your different vehicles to serve the request. The difference is basically at the beginning of the day, you don't know the request you will have. And so at every epoch, let's say every half an hour, you are going to send a wave of trucks to serve your request. And for some requests, you still have time to serve them. So you have to ask yourself the question, do I serve it or don't I serve it? And the second thing is you have to decide which routes you are going to do, okay? And then you have served these requests, they disappear, some new requests appear, and you take the same decision and you iterate until the end. And so basically your objective is to find a policy that, given the current state, that is the set of unserved requests, map these to the requests you are going to solve now and the routes to serve them. So typically it's, and the goal is to minimize the expected cost of serving everyone because you are going to serve everyone. So this was the topic of the EURO-NeurIPS challenge in 2022. And the way we solved it was the following. We observed that the decision, the output we have, is basically
the set of feasible solution of a variant of the capacitated vehicle routing problem, where basically serving a request is not mandatory, but if you serve a request, you get a prize for serving it, and your goal is to maximize your profit, that is the sum of the prize you collect by serving request minus your routing cost. The thing is, you do not have, so you know the routing costs in your true problem, the dynamic one, but you have no idea of these prices. That's something artificial. And what we are going to use is a neural network, a graph neural network, to predict these customer prices. So basically, we build a sparse GNN on this, and we predict prices for each of the requests. And then this is a variant of the capacitated vehicle routing problem. Trust the combinatorial optimization guys. They have been made very efficient deterministic algorithm for this, for instance, a hybrid genetic search. So that's what we did at the policy. And we were surprised to win the challenge with a significant advance on the second team. And we have now replicated that on roughly 10 dynamic problems in OR. It feels that when you have basically a Markov decision process where both the state and the decision are combinatorial and in very large dimension, which is a case that is not really well treated by either stochastic optimization, multi-stage stochastic, which needs small dimensional state, or reinforcement learning, which means which needs small dimensional decisions. Basically, in that case, this happens to be pretty efficient. And so these are the main kind of applications we have in operation research, where we want, well, either for contextual stochastic optimization or for dynamic problems, these graph neural networks, when you add a combinatorial optimization layer, can be game changer. So the question is now, how do you train them? And to train them, for this to work, you need to train them in a decision-focused learning way, which means your loss is not going to be on the input of the combinatorial optimization, but not of the output, really the why you are getting out at the end. And so typically, the goal, in the supervised learning case, I go slightly more general. I guess that I have a distribution over X. I have a decision Y that must be in Y of X. I have a cost function for this. So this covers, for instance, the contextual stochastic optimization case. And I seek a policy that maps X to Y that is going to minimize the expected cost. Okay? And my policy will always be a graph neural network followed by a combinatorial optimization layer. And to train this, basically, I have two main paradigms. The first one is supervised learning. Okay? You assume you have a training set with both instances and target solutions to imitate. And in that case, basically, we can use things that have been developed by machine learners 10 years ago. And then there is the empirical cost minimization, where your training set, you just have instances. You have an array call to evaluate C0, that's all. And what you want to do is to minimize the empirical cost, where basically the empirical cost where this is the output of your neural network. Okay? And so I'm going to introduce algorithm for this. And there is a big challenge because, well, you want to use a graph neural networks, or you are going to use a first order method with automatic differentiation to train the GNN part. The problem is the following. Look at your combinatorial optimization layer. Okay? Let theta be in the input. Theta is the direction of your linear program. Let's say that while theta is in the normal cone of y1, then the output of your layer is going to remain y1. Okay? So from a polyhedral point of view, your layer is piecewise constant on the normal fan of your combinatorial optimization layer. Which means both for empirical cost minimization or for supervised learning, you get a loss that is piecewise constant. So your stochastic gradient are not going to bring you very far away. And so we need to get meaningful gradients. And the main strategy consists in regularizing. Okay, so we add a strongly convex function to push the optimum in the interior of your polytope. And when you do that, basically, it's going to evolve smoothly with theta. and you get basically a loss function that is going to be a smooth piecewise constant. So if you do this, it's going to work a little bit, and you just have to look at this landscape to understand why. Basically, a gradient descent on this is going to end up in a bad local minima. The next idea is just for supervised learning. Okay? For supervised learning, you have this idea that, okay, now I'm going to do a primal dual loss. Theta is my direction, okay? And basically, max theta dot y it just gives me a solution. If I have theta, I have y, okay? I can know how to go from the dual to the primal. And y bar is going to be the optimum of my problem for theta, okay? If y bar is equal to max theta dot y. So what I want y bar to be the optimum of this problem. And so it's natural to take as the loss the non-optimality of my target as for the combinatorial optimization layer I use. And I'm going to use as a loss this, and when I regularize, I recognize on that part basically the Fenchel conjugate of omega, and so my loss is going to be the left-hand side of the Fenchel-Young inequality. This tells me that basically my loss will have all the good properties I want, and especially it's going to be convex in theta. I know its gradient, they are tractable, and if I regularize, it's going to be smooth, and it's going to be zero only in the interior of the normal cone of my solution. So basically, it's going to behave pretty well. And if I continue with this, basically, if I think about Fenchel conjugacy, okay, omega is going to be a mirror map. That is, it's going to induce a bijection between the space of theta, the direction of your linear program, and the space of mu that are the moment and the interior of your polytope. Okay? And if you look at the Fenchel-Young loss we use, so for instance, the distance between theta and the moment mu bar, it's equal to a Bregman divergence between mu bar, your target, and mu, that is the one predicted by your layer. Okay? So basically what we do when we minimize the Fenchel-Young loss is just we minimize the Bregman divergence between the prediction of my graph neural network with a CO layer and my target. Okay? But it's far more convenient to express it in a primal dual way. Why? Because this way you are convex in theta, and so you have a loss that is very comfortable, and your stochastic gradient descent converges very well. Practically, this has been done, introduced a bit more than 5 years ago by people like Mathieu Blondel in the machine learning community. This works very well, but so does this solve everything? Well, in the supervised learning and the machine learning community, it's very useful to have this, but in the operation research community, we are pretty interested in the other regime, which is the empirical cost minimization. And the reason why we want to do empirical cost minimization is twofold. First, on many cases, we do not have a good expert, so we don't have a training set with Y to imitate. And the second is that it enables to get generalization guarantees I am going to explain. So now I'm going to consider the empirical cost minimization in the contextual stochastic optimization setting. So I'm again in the contextual stochastic optimization setting, where X the context, Xi the noise, and I have a training set with pairs of Xi and Xi. So Xi is the context, the weather forecast, and Xi the delay that realized for my airlines. Okay? And I make the hypothesis that I have an efficient algorithm to solve the problem when it's not stochastic, when I have full information. Okay? When a new instance arrives, well, I have the weather forecast, but I don't know the delay when I take my thing. And well, at the beginning, it started with we just wanted to do a simple coordination heuristic. Okay? So what's the idea behind the heuristic? Imagine, well, you solve the problem independently for each training point. Okay, so you overfit the delay, and you take the best decision for xi for this delay. Okay, so this is going to be to overfit it. And this way I can apply the supervised learning approach I have mentioned just below. So my neural network is going to predict a solution. Okay, and the solution is different from because I had to average over my training set from the best solution that is for my scenario. Okay, and one question could be, okay, now perhaps we should try to coordinate the different scenarios. Okay, so I want to update y bar, my target. It's not going to be the best decision for only this scenario that overfits xi I. It's going to be an average between my cost, the true cost for that scenario, and what is predicted by my GNN. In other words, I use my GNN to coordinate the different scenarios. And we implemented that heuristic, and it worked pretty well. So basically, you iterate. Basically, you learn with your targets. You update the targets to coordinates. You learn and you iterate 10 times, and we observe that it works pretty well. And what we understood 2 years later, that it was in fact an exact algorithm. And to explain this, and basically it scales extremely well. In fact, if you compare to, for instance, using on a stochastic optimization problem, a Lagrangian relaxation approach, it converges much faster and it scales pretty well. So now let's yeah.
In what sense is this an exact algorithm?
I'm going to give the theorems and explain in what sense it's an exact algorithm. The first thing I would like to observe, so look at the optimization problem of your layer. Okay, you can express this in small dimension, no problem. A second thing you can do is to have the equivalent problem is to optimize over the distribution over Y. So delta I is the simplex, the probability simplex over my combinatorial large set Y. Okay. And what I can say, and theta dot y, so this is just the thing matrix. Basically, this is going to be a vector with for each coordinate. Basically, the theta dot y. It's the value of the objective for y. Okay, and basically, if I optimize this, the optimum is going to be a Dirac in the optimal y. Okay, so these two problems are equivalent. And if you do polynomial optimization and moment, basically that's a trick that you use a lot. The second thing I need is, okay, I can go to this distribution space that's going to be huge in dimension, let's say 10 to the power of 100. So I cannot do computations there, but at least theoretically I can do it. And I can do this regularization that gives me a bijection between the distributions and the dual of the distributions that are the objective functions. Okay? So now I have something that maps any objective function, among which the linear y, that's the linear ones that I get like that, with distributions over my solutions. And now I'm going to reformulate my problem on this high dimensional space. Okay? So now, basically my cost function for a scenario xi, I, okay, is in the space of cost functions. It's not in the on the hyperplane of linear objective functions, but it's in that space. Okay? And if I take the distribution, so this is going to be the distribution that is predicted by my neural network. Basically, the expected cost is just the scalar product between the distribution predicted and the true cost function in that space. Okay? So that's just a reformulation of my problem. And the second tool I am going to use is to say, okay, instead of just minimizing on the parameter of my neural network, okay, I will do a relaxation. Okay? The relaxation I do is that I say now I am free to choose the distribution for every qi. It's no more the one predicted by my neural network. But I add a penalization term that is a Fenchel-Young loss between the distribution I choose freely and the prediction of my neural network. Okay? So if I send kappa to infinity, basically I will want to drive this to 0, and I will recover as q the prediction of my neural network, and I get back on the initial problem. If kappa is smaller than infinity, basically this is a relaxation of my initial problem. Okay? And now if I do that, basically, and I look at this surrogate problem, the heuristic I gave before is very close to, and I will explain why, to an alternating minimization algorithm where on one step I minimize over Q at W fixed, and on the other step I minimize on W at Q fixed, okay? When I minimize at W, basically this is constant and I get a supervised learning problem in Fenchel-Young loss. The guys from Google DeepMind have done very efficient algorithm for that for 10 years. This, basically, it's minimizing the expectation of a cost plus a Fenchel-Young loss. This looks pretty complicated at the beginning, but it decomposes training point by training point, okay? And the proposition that we made is that, in fact, this is tractable, and I'll explain why. But before this, I'll give, now I can give a sense to how it's an exact algorithm, okay? The first thing is provided some technical assumptions. The iterates you have, okay, coincide with those of mirror descent for another function. The function that you get when you minimize over S, you get a function that depends only on Q when you minimize over your score, okay? So this is minimizing on W, on your neural network. And the second thing we are going to show is that if we choose the right regularization, so it's the mirror descent iterates for this problem, and this function is convex. So basically, mirror descents converge to the optimum. So this is going to tell you that you are going to converge to the optimum of the surrogate problem. The second proposition we have is that now when we minimize over Q instead of minimize over S, so the other thing, basically we can bound the distance between the objective of the initial problem, the empirical risk minimization, and the objective of the surrogate. Which means that since we can bound the distance between the two functions, we control how far we are from the optimum. And the last theorem is a statistical learning generalization theorem that tells you that basically if your data sets becomes large enough, you are going by minimizing to the optimum of the empirical risk minimization, you go to the optimum of the empirical risk. Okay? So it's in that sense that we have an exact algorithm, and I am going to precise this a little bit. So the first thing is, okay, which regularization do you use? Maybe one of the main contributions to the topic was a paper from Berthe et al. In 2020. In the supervised learning case, they show that basically if you take as a regularization the Fenchel conjugate of the perturbed maximum, okay, so Z is going to be a Gaussian random variable, well, you get a well-defined mirror function with very nice property, and the very important property is the following. It's the gradient of your thing is going to be the expectation of the argmax. In other words, basically, when applying the regularized problem, you just have to sample a few Z and apply linear optimization. So it applies whenever you have an array call for your layer, it works. What we have proved is something more general, is that this regularization can be extended in the distribution space, which surprised us at the beginning. So you take just a linear regularization, okay, with Gaussian environment, it still works and you have all the same properties. Once you have done this, basically you can prove that your decomposition step is going to be the expectation of the argmin of your costs for your given scenario, plus something linear. So you just have to sample a few Z and you have a stochastic gradient, and so you know how to evaluate it. Okay? For the mirror descent, that's what I explained before. The surprising thing is that basically when you minimize over Q, over S, over your score, that is over your graph neural network, what you get is basically your objective function plus the Jensen gap. And surprising, so if you take an arbitrary convex regularization omega, this is going just to be positive. But for the regularization we are interested in, this happens to be convex. And so as we have narrow descent for this function, we converge to the optimum. There is nothing particular in the proof of the other results that bounds the error between the surrogate and the risk, just that you control this, and so you can optimize over that. Just one thing now about statistical learning and the generalization you are going to get with such an approach. So the thing I'm interested in is basically I'm going to solve my empirical risk minimization problem, and can I say something on new instances that are not in my training set? Actually, so don't read everything. I just want to show that you can decompose your error into several terms. One on which we don't know how to do anything, it's the model bias. The idea is if you choose a bad architecture for your GNN and a bad combinatorial optimization layer, you can have the best learning algorithm. This model bias is, even the best policy encoded by your neural network is going to be poor. Then there is an error that comes from the regularization. An error that comes from empirical process, basically the fact that you sample and you can bound it using classic techniques. And an error that comes from the optimization in your algorithm you use to solve your empirical risk minimization, the alternating minimization algorithm. So I've explained before that basically for this we show that we can drive it to 0. And using statistical learning approach, we can bound the two other parts. In other words, if you optimize over the constants, you can show that in the large dataset regime, you converge to the best policy according to that is encoded by your neural network. An important question where we would need some, what we would like to work on, well, there are two important questions. One that is, okay, can we have some universal approximation theorem that shows some bounds on this model bias? We have nothing on this. And the second is, we do not treat out of distribution generalization, and notably can we use ideas like Graphon to say we train on some small instances and generalize on large, which is, by the way, what we do on every application. We train on an instance of size, for instance, on the airline application, we train on an instance of size 50 and generalize on an instance of size 5,000. Now, just going, so how to learn for dynamic problems. So I go back to my dynamic vehicle routing problem, okay? Basically, the simplest thing to do is to use supervised learning with Fenchel-Young losses, okay? The thing is, for this, I need a training set with states and targets, okay? So how do I generate it? The thing we did for the challenge was pretty simple. It's just observe that if I place myself at the end of the day and I have all the data, it's just a classic capacitated vehicle routing problem. So we solve it with our favorite capacitated vehicle routing problem, and we rebuild the decisions that we would have taken at every time step to this. This gives us a training set of anticipative states and decisions, and we imitate it. That's what we did on the challenge, we happened to be pretty lucky because, well, it was a total surprise for us that we won, and the first thing we tried to do is to replicate on many other problems. And on almost all of the other problems, we get relatively poor results. And we understood that there was one key ingredient that you must add for this to work. It's that basically what we did is we imitated a good policy, okay, on the states that are generated by that policy. The thing is, since it's an anticipative policy that uses information that is not available at the moment you take it, you cannot imitate it perfectly. And what we want is to imitate it on the states that are generated by our policy, okay? And this can be pretty far away because since this uses information that you don't have access to, basically this can be pretty far away from this. And so the things we had to change is basically to correct the training set with states that are close to this. But this is a classic problematic in reinforcement learning. And for instance, if you regenerate your training set by applying sometimes the anticipative policy and sometimes your policy, it works very well, and there are some other approaches. And in fact, we can understand why does this work well in practice. Well, in multi-stage stochastic optimization, something very simple policies that work well are voting policy. You sample a few trajectories from the current state, okay? You solve them, each of them independently, and you take the average decision. So if your decision is the quantity of water to turbine in your dam, that works very well. If it's routes, of a vehicle rating problem, then you have a problem, because since it's combinatorial, they are most likely completely disjoint, and so, well, you have an average of disjoint routes, you don't know what to do. But in fact, learning in doing supervised learning with a Fenchel-Young loss is just a generalized maximum likelihood estimator to train a conditional distribution over your routes. And you know how to sample it. So basically what we do is a voting policy where we average across states. And that's the reason why it works pretty well. Still, that's not the end of the story, because there are cases where the anticipative decisions are really poor, and in that case, imitating them doesn't work. And something that is more important is that on many cases you are in a reinforcement learning setting, in the sense that you have never access to XI. Suppose, for instance, that you are doing pricing, okay? You don't know what the customer would have done if you would have put other prices, okay? And so in a reinforcement learning setting, first let's do it single step. You have access to an evaluation or Ecole. Basically, you set up your prices, you see if the guy buys or not, and you get a cost. But you definitely not have a combinatorial optimization or Ecole, even when this is fixed, because you don't have access to that, okay? You just observe C. And so we wanted an algorithm that is able to learn in that context. And the reason why we cannot apply our alternating minimization algorithm is that the decomposition step is not tractable anymore. Why? Because remember, we had the expectation of this minimization of your cost for a given Xi, and I just told, well, we don't have access to this information. We don't have we just can evaluate that cost, but we can certainly not minimize on this. Okay? And so how do you update this algorithm to have a tractable decomposition step here? And an idea happened to work very well in a generic context. Okay, so the problem is basically you are optimizing over your polytope, which has far too many vertices, let's say 10 to the power of 100. But your GNN encodes a conditional distribution over these vertices, okay? So what you can do is just sample a few vertices, okay? And what you can do is that now you can restrict the optimization to these vertices sampled from your distribution, okay? And now it's tractable, because if I have sampled 10 vertices, I can apply my evaluation oracle on these 10 solutions and take the best one just by brute force optimization on a space of size 10. And so that's exactly what we did on our structured reinforcement learning algorithm. It's the same thing as the alternating minimization algorithm, but instead of doing the true optimization over all my solutions, combinatorially large, I sample a few plausible solutions from my current policy and optimize over this one, which I can do. And so, okay, so this gives you the single-step reinforcement learning, the static. How do you go dynamic? Basically, you embed that in an actor critic algorithm, okay, where your GNN with a combinatorial optimization layer is going to be your actor. You use a critic, again a GNN generally, but there is nothing special on that critic, and we update it in the usual actor critic setting. The big difference is that we update our actor with this alternating minimization algorithm plus sampling I have just detailed. And when doing that, basically what we have seen is that it works surprisingly well, in the sense that basically the structured reinforcement learning algorithm was able to learn almost as well as the imitation learning in cases where we have experts that are the optimal decisions. And when the expert, we do not know a good expert, basically we were able to beat it and to beat all the things we had. And what was surprising is that it converged reasonably fast. And what is hidden behind that is that during the 3 years before, we had implemented almost any classic reinforcement learning algorithm like PPO, soft actor critic, and things like that to train this neural network with combinatorial optimization layers. And we never managed to make any of these one work. And the reason for this is that all of them with our networks amount to a reinforced gradient, which is extremely noisy, whereas doing this primordial approach leads to a reformulation trick gradient that is much less noisy, and that's the reason why we learn. So in summary, if you like GNN, basically adding a combinatorial optimization layer at the end is interesting because it enables to address important applications in operation research for which there was no good methods previously. The supervised learning things that have been developed in the structured learning community, typically for vision between 2000 and 2010, and then by people at Google for recommender system after 2015, made the work for us for all the supervised learning part, but they used, as a combinatorial optimization layer, they used mainly matching and sorting, whereas we have been using any combinatorial optimization algorithm that you can imagine in operation research. What is new on this is the empirical cost minimization. And basically, it leads to practically better policies. And since it minimizes the empirical cost, you can prove generalization results, which was not possible for that. I didn't talk about it, but we are maintaining a full ecosystem of automatic differentiation. So everything that implementing the algorithm is not that complicated because we have done the job for you for the automatic differentiation. And if you like graph neural networks and combinatorial optimization and stochastic optimization, then this is a nice topic to work on. Thank you very much.
Questions? So I have a question, but you were talking about a few technical results for technical assumption to actually guarantee in the proof that the convergence there. Are these technical assumptions very restrictive, or they are okay?
Yes, in the sense that, what is restricting and what is not restricting? Basically, the main assumption you have is that we need the thing to be convex. So for a general graph neural network, just forget about it, okay? We didn't express it like that in the paper, but basically there is a relatively classic setting for this kind of proof where you think that, which is the mean field regime, where basically you have a single layer with an infinite number of neurons, neural network, then you prove that you go to the optimum. Mm-hmm. Okay, so and it's a relatively classic setting for doing proofs of this kind of results.
But this means that, I mean, in a, let's say, in a practical setting in which you don't have infinite things, so are you observing like serious deterioration, or more or less you just...
No, I mean that's the elephant in the room. In the deep learning, basically, if you are using any nonlinear neural network, we don't know that it converges to the optimum, but in practice it converges pretty well. That's what we observe. Basically, in fact, we observe rates that are extremely close to the theory with a general GNN. But we don't know how to handle non-linearity there.
This is a different story, yeah. Other questions?
Yeah, one quick question. Do you have a litmus test of when to use GNNs for the prediction before the combinatorial optimization as opposed to other techniques? Like when do you decide to use
GNN there?
Yeah.
In fact, we don't have a thousand of choice in the sense that basically we want to train on small instances and generalize on large instances with graph that changes. So basically, architectures that take input of variable size that are most of the time labeled graph and that get an output of variable size too. Apart from GNN, well, you don't have that many architectures. And so if you have ideas of other architecture than GNN or simplification of GNN, I am very interested. It's just that we didn't know what to use apart from that. Yeah.
So, I have a question regarding the idea of how to use this. So I guess one of the, most of these applications are decision-focused learning, right?
Yes.
But have you thought about using these architectures to just simply accelerate the solution? So if the predictor is, or the graph neural network predicts some useful information to solve a more compact
Yes, in fact,
problem?
We are going, so there is nothing published now, but at least 3 papers are coming in that respect. The main use of it is that the decomposition method you use here, you can use as an alternative to other decomposition method in mathematical programming. And we have observed that it tends to converge much faster than Lagrangian decomposition, relaxation, or things like that. And so that's, and in fact, typically, the first thing we did was inventing the heuristic at the beginning, which is close to it, just as a decomposition method for a problem we didn't know how to solve. So yes, it works very well. And Fenchel-Young loss has Bregman divergences that give nice metric, that's what I'm going to say if it's not a metric, on that captures the structure, the geometry of MILPs. I think it's a promising idea.
Other questions?